Today we'll be discussing applications of thermochemistry. Keep in mind as a review that we have some favored conditions when we deal with thermochemistry. Favored conditions include a positive delta S. A positive delta S is entropically favored. A negative delta H is thermodynamically favored. You can't say that delta S is, a positive delta S is thermodynamically favored. It's not thermodynamically favored. It's entropically favored. Delta H, on the other hand, if it's negative, is thermodynamically favored. If a particular reaction has a negative delta G, it is always favored. And if these signs are switched, if we have a negative delta S, a positive delta H, those always have a positive delta G, and therefore would be an unfavored situation. We run into a quandary, however, when we have the same sign for both delta S and delta H. If they're both positive or both negative, then we need additional information before we can determine whether they are favored or if that reaction is favored or not. We can use the equation delta G equals delta H minus T delta S. Remember, we often write it in class as delta G equals delta H minus delta ST, just because it looks like ghost, and we like to call it the ghost equation. But keep in mind that, let's say we have a situation where we have the same sign positive for both delta H and delta S, and that because of this, delta G is positive. And we want to find a way to turn this into a favored reaction instead of an unfavored one. Temperature is the factor. We can raise or lower the temperature in a chemical reaction and change this. In this case, if we raise the temperature of this reaction, we make this term bigger, which means we're subtracting a bigger term. If we're subtracting a positive term from delta H, then if it gets big enough, it will turn delta G into a negative term. So again, by increasing a positive situation, increasing the temperature on a positive delta H, positive delta S situation, we can make delta G turn negative, increase the favorability of that reaction. On the other hand, if we have a negative delta H and a negative delta S, and because of that, we have a positive delta G, what that means is that when we subtract that negative term, this term right here is too large. We need to decrease that term so that that overall term is not so positive. So if we decrease the temperature, we're going to make this term smaller. So we're subtracting a smaller negative value, and therefore we can cause that negative delta H to take over and turn our reaction negative. So recap. Positive situation, increasing temperature can make it turn favorable, can cause delta G to become negative. If we have a negative situation, negative delta H, negative delta S, by decreasing the temperature, we can accomplish the same thing, change delta G into a negative value in many cases. Now, the reaction we're looking at here is a reaction, the equation we're looking at here is an equation that we deal with for gases only. And delta G is the free energy value when we're not at equilibrium. Excuse me. Delta G0 is a value that we use when we're in all standard situations. We have all standard conditions. If we are at equilibrium, delta G is 0. During a phase change, delta G is 0. So those are two things you need to remember. Remind yourself that Q is the reaction quotient, and this is only for the partial pressure of gases. It's only for those. And remind yourself that we find Q the same way we find K, products over reactants. R is the gas constant. If we're dealing with delta G, we need the joules per Kelvin mole because delta G is the free energy. T is for the temperature, and it must be in Kelvin since we're dealing with gases. And again, delta G0 is the free energy under standard conditions, 1 atmosphere. So let's look at our examples. First thing it asks us to do is to calculate delta G for the following reaction if the reaction mixture consists of 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 1 atmosphere of ammonia at 25 degrees Celsius. And it gives us delta G at negative 33.32 kilojoules per mole. So it gave us delta G and delta G0, and it gave us values of pressure for each of the substances listed in the equation, which means we can find Q. So that should be our indication that we're dealing with our delta G equals delta G0 plus RT times the natural log of Q. We're supposed to find delta G. It gave us delta G at negative 33.32 kilojoules per mole, but since R is in joules per mole, we're going to go ahead and change this to joules per mole. So 33,320 joules per mole plus R, which is a quantity, R, 8.3145 joules per mole Kelvin times the temperature, which is 298 when we add 273 to our 25 degrees Celsius times the natural log of Q. So we need to find Q. And in a separate calculation, we see that Q is going to be the pressure of the nitrogen squared divided by the pressure of, that above one was the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed. It gave us the pressure of ammonia as 1.0 atmospheres, the pressure of nitrogen as 1.0 atmospheres, and the pressure of hydrogen as 3.0 atmospheres, and that has to be cubed. So we're looking at 1 divided by 27, which is 0.037. So coming over to our equation, we need to find, in this case, then, the result. We take negative 33,320 joules per mole, 8.314, and go ahead and add the 5, joules per mole Kelvin, times 298 kelvins, times the Ln of 0.037. When we work that out, we get a value for delta G of negative 41,500 joules per mole. It did not ask for it, so usually I'm pretty fond of just leaving it in the original units, but we can go ahead and say that this is 41.5 kilojoules per mole. Now going on to the next example, it It tells us that we have a reaction in which mercury liquid is going or in equilibrium with gaseous mercury, and that we have a delta H value of 61.3 kilojoules per mole and a delta S value of 100 joules per Kelvin mole, and it wants to know the normal boiling point. So it looks like we need some kind of a relationship between delta H, delta S, and temperature, and we find that a great equation that involves those, and pretty much the only one we know is that delta G is equal to delta H minus delta ST. And when we look at this problem, we see that we're given a delta H value, we're given a delta S value, and we're asked to find the boiling point or temperature. However, the problem is that we don't have a delta G value. Or do we? Look back up at our reaction, and we see that going from liquid to gaseous mercury is simply vaporization. Vaporization, remember, is just a phase change, and looking above in our notes, we see that if we have a phase change, what is delta G? 0. So that takes care of that variable. So now we're left with an equation that is going to end up with only one variable. So let's plug those values in. 0 for delta G. Delta H is 61.3 kilojoules per mole. Please don't forget that when you write in delta S is virtually always in joules per Kelvin mole. And you want to make sure that you change that. I'm going to go ahead and change that to kilojoules. So 0.100 kilojoules per Kelvin mole. And we're trying to find T. Now, I always like for my variables to be positive, so I'm going to take that subtracted term and move it and add it to the other side. So I'm going to end up with 0.100 kilojoules per Kelvin mole times the temperature is equal to 61.3 kilojoules per mole. And when we solve this, simply going to divide both sides by 0.100 kilojoules per Kelvin mole. And when we do, we end up canceling it on this side, or reducing it to 1, as my math friends like me to say it. Kelvins ends up at the bottom of the bottom term, which, remember, means it's on top. I have a shortcut there, but what we end up with is 613 kelvins for our answer. The question didn't ask for it, so I would suggest just leaving it at 613 kelvins, but just for practice, remember that we can get degrees Celsius simply by subtracting 273, which will give us 340 degrees Celsius. So that takes care of that problem. So let's look at our final example. And in this case, we are at equilibrium. And when we are at equilibrium, delta G0 is equal to negative RT times ln of K. It just kind of rearranges that previous equation. We've pretty much always called this the Ratlink equation. Delta G equals negative Ratlink. We call this one of the meaning of life equations because in chemistry we have some major areas. We have thermochemistry, we have electrochemistry, we have equilibrium, and there are a series of equations that relate those three areas of chemistry together. And this is one of those equations. It relates thermochemistry, our delta G value, with equilibrium, our K value. So when I look at this example and it says calculate the approximate standard free energy for the ionization of hydrofluoric acid, HF, and it gives me a Ka, I automatically think thermo and equilibrium. And I think meaning of life equation. And which one am I going to use? The delta G equals negative Ratlink. We are trying to calculate delta G. R, once again, since we're dealing with free energy, the R should be our joule value of 8.3145 joules per mole Kelvin. The temperature is 25 degrees Celsius, standard temperature for thermo, or 298 kelvins, which it must be in this equation. And our natural log of 1 times 10 to the minus third. And when we work this out, we come up with a value of 17,115. Now we can leave this in joules per mole, but if we do leave it in joules per mole, we want to make sure we still think about sig figs. 1.7. And to the 3 sig fig rule, if you want to use a 3 sig fig rule for your AP problems, 1.71 times 10 to the 4th joules per mole. And if you just can't stand it and not put it in kilojoules per mole, it ends up being 17.1 kilojoules per mole. And that concludes today's discussion.